Well, good morning, everyone. It's Mrs. Price again here with 6.4, which is more information about finding solutions of polynomials. Today, we're going to focus on synthetic division. We're also going to learn the rational root theorem, and we'll spend a minute or two kind of touching on how to do long division with polynomials as well. Let's get started. So this first problem asks, what are the zeros of this huge fifth degree polynomial? So the first thing it instructs us to do is to take a look at the graph, which I've already entered into Desmos. You can type it in Desmos yourself or type it in your graphing calculator and take a look. So if we take a look at the graph, well, let's see, we want the zeros. Zeros are the same thing as x-intercepts on the graph. Let's take a look. So we've got an x-intercept at 1, 2, and 3. So we have zeros at x equals 1, x equals 2, and x equals 3. Why are they called zeros? Because when x is 1, y is 0. When x is 2, y is 0. When x is 3, y is 0. So that's why they're called zeros. They're also called roots, and they're also called x-intercepts. The question asks, what do we get when we substitute a 0 in for x in our polynomial? Well, let's just see what happens here. So if I substitute a 1 in for my x, so I replace all my x's with 1, I get 1 minus 6 plus 20 minus 60 plus 99 minus 54. And if you enter all that in your calculator, you're going to get 0, which of course makes sense because we just saw that when x equals 1, y equals 0. Y is the output to our function. So, of course, p of 1 is 0. And then by the same token, p of 2 is going to equal 0, and p of 3 is going to equal 0. So whenever we substitute any of the x-intercepts for our polynomial into our function, we're going to end up with an answer of 0. What is this called? This is called the remainder theorem. So the remainder theorem says if x minus r is a factor, which means x equals r is a root or a solution or an x-intercept or a 0, then x minus r is a factor only if p of r equals 0. So only if you plug the r into your function is your output 0. Then, of course, x equals r would be a root or an x-intercept, and then x minus r is a factor. However, for our problem, this was a fifth degree polynomial. When you have a fifth degree polynomial, there need to be 5 zeros. How many did we find? We found 3 of them, which means there's still 2 more that we haven't found. How do we find those remaining 2 zeros? And why aren't they shown up on the graph? Well, only the real zeros will show up on the graph, so as x-intercepts. So if we have 1, 2, 3 x-intercepts on our graph, but we have a fifth degree polynomial, that means that there have to be 2 imaginary zeros. So 2 additional complex zeros that have an imaginary component must be a part of this function. How do we find what those are? Well, we have to divide out the other zeros. So when we divide, what we're technically doing, remember that this polynomial is the same thing as a product of a bunch of factors, right? We can write this as a product of a bunch of factors. So if we want to get rid of one of those factors and see what's left, we're going to divide the whole polynomial by one of those factors. So for example, we know that 1 is a 0. X minus 1 would therefore be a factor. We're going to divide it out and see what's left. And we're going to use a process called synthetic division. Synthetic division is really fun. I think you're going to like this. So the first thing you do is whatever your divisor is, you set it equal to 0 and solve. And of course, we already knew that x equals 1. So it's the actual 0 that we put into a little corner bracket here. Then going across, what we're going to write are all the coefficients of all the other terms. So we're going to list all these coefficients going across. So our x to the fifth coefficient is 1. Then our x to the fourth coefficient is -6. X cubed coefficient is 20. Then -60. Then 99. And that's a 99. Finally, -54. We're going to leave a little space and we're going to draw a line. By the way, little note, if any of these terms are missing, for example, say it had -6x to the fourth and then jumped right to -60x squared and there was no x cubed term, you would have to fill in a coefficient of 0 for that. You can't have any missing terms going across. Okay. So here are your steps. The first step is always to take the very first coefficient and just bring it down. So I always yell, like whatever my number is here, I yell, bring down the 1. It's kind of like bring out your dead on Bring Out Your Dead Day. Bring down the 1. So now we're going to do ma, 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 kind of like what a baby says over and over. Ma, ma, ma. I can't write with this stylus. That's a ma. Ma, 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 ma. So what does ma, 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 ma stand for? It means we're going to multiply up and add down. So we take the number that's down here and we multiply it by whatever number is in our bracket here. So 1 times 1 equals 1, and we put the answer here. Then we add down and we get -5. That's our first ma. Now we take this, multiply up, -5 times 1 is -5, put the answer here, add down, multiply up, 15 times 1 is 15, add down, -45, multiply up, add down, multiply up, whoops, I can't write, add down. This last number is always the remainder of your division. It's the remainder. It does not count as a part of the quotient. It is the remainder, which means if this is a 0, then this remainder had better be 0, otherwise you've done something wrong. So if you know 1 is a 0, your remainder has to be 0. Now, how do we write the quotient? How do we write the actual answer? What polynomial is left when we divide our original p of x by x minus 1? Well, if you notice, we were dividing a fifth degree by a first degree. So what happens is we essentially subtract 1 from all of our exponents. So now these numbers are the coefficients of a fourth degree polynomial. We've reduced the power by 1, and so now our polynomial is fourth degree, and our first coefficient is 1x to the fourth, then -5, and you just go down, x cubed, plus 15x squared, minus 45x, and then finally plus 54. And there's our quotient. All right, but we are no closer to getting to those two complex zeros. I don't know how to factor this thing. How do we find those last two complex zeros? We're going to have to synthetically divide again, but it's going to go faster this time. So we're going to go ahead and go to the next page, and we're going to divide x equals 2 out of this quotient right here. So I'm going to rewrite x to the fourth minus 5x cubed. Forgive me if I go back and forth a little bit. So I have x to the fourth minus 5x cubed plus 15x squared minus 45x plus 15x squared minus 45x plus 54. All right, so this is our quotient from the previous page. I'm going to divide this by the factor x minus 2. So what number goes into my little bracket? I set my divisor equal to 0. I get x equals 2. I put a 2 in my bracket, and then I start listing my coefficients. 1, -5, 15, -45, 54. All right, bring down the 1. Multiply up. 1 times 2 is 2. Add down. Multiply up, add down, multiply up, add down, multiply up, add down, and thank goodness, again, our remainder is 0, which it's supposed to be because we knew that 2 was a 0. And so now these are the coefficients of our quotient. So our new quotient, the remaining polynomial, remember we reduced the degree again by another 1, so we're going to have 1x cubed minus 3x squared plus 9x minus 27. Now, to figure out what's left, you could factor this by grouping, but I'm going to go ahead and synthetically divide out the last number, the last 0 that we knew, which was 3. So I'm going to have to rewrite this, x cubed minus 3x squared plus 9x minus 27. So x cubed minus 3x squared plus 9x minus 27. We're going to divide this by our final factor that we knew of, which was x minus 3. So I'm going to set x minus 3 equal to 0. I get x equals 3. I put that in my corner bracket. I bring down my coefficients. Leave a little space, draw a bar. Bring down the 1. 1 times 3 is 3. Negative 3 plus 3 is 0. 0 times 3 is 0. 9 plus 0 is 9. 9 times 3 is 27. Negative 27 plus 27 is 0. That's our remainder. So let's write what's left. Remember, we have now a third degree divided by a first degree. So this becomes the coefficient of an x squared term. So our new quotient is 1x squared plus 0x plus 9. So there's our quotient, x squared plus 9. So if I want to find my 2 remaining zeros, I can just set this equal to 0 and solve. So if I subtract 9 from both sides, I get x squared equals negative 9. I'm going to take the square root of both sides. Make sure you put a plus or minus in front. I get x equals plus or minus the square root of negative 9. But that's the same thing as plus or minus root 9 times root negative 1, which is the same thing as plus or minus 3, because square root of 9 is 3, and the square root of negative 1 is I. So our final answer, our zeros for our polynomial would be at 1, 2, 3, 3i, and negative 3i. If we wanted to write our polynomial in factored form, let's see if I can fit this in here. Our polynomial would be x minus 1 times x minus 2 times x minus 3 times x minus 3i times x plus 3i. And there's our polynomial in factored form. Okay, we're going to learn a new theorem called the rational root theorem. Kind of a funky theorem here, and we're going to talk about P's and Q's. So in this case, what it says, say you've got a big polynomial and you can't graph it. Or suppose you can graph it, but all the zeros fall in between integers. They don't just fall nice and pretty on specific integers. They're in between and you have no idea what the numbers are. Is there a way algebraically to figure out what they are? Well, the rational root theorem is what helps us figure it out. So what it says is all rational roots must be of the form P over Q, where P is a factor of the constant term and Q is a factor of the leading coefficient. So what you end up with is all the factors of the constant over all the factors of the leading coefficient. All possible factors, positive and negative, have to be considered. And remember, this only gives you possible rational roots. It doesn't give you irrational, it doesn't give you imaginary roots, and every number that you find is not necessarily going to be a root. So it's probably going to give you a ton of numbers that aren't roots. So it's not a real slick theorem. It gets a little cumbersome, but it is a helpful theorem. So let's see if we can use it. So we're going to find the roots of this cubic polynomial here. So we're going to start by listing our possible rational roots. So our constant term, our p, is 25. That's the constant. Don't worry about the negative. We'll deal with the negatives in a little bit. And our q, that's the leading coefficient, that's 3. So the possible rational roots are all the factors of 25, factors of 25 over all the factors of 3. So let's just start by listing those factors. 25, all the numbers that go into 25 evenly are 1, 5, and 25. The numbers that go into 3 evenly are 1 and 3. All right, so if we had to divide all of these by all of these, let's start with 1. So our possible rational roots, and I'm going to leave a little space in front of each number. There's a reason why. So 1 over 1, 1 over 3, 5 over 1, 5 over 3, 25 over 1, and 25 over 3. It's all of these divided by all of these. So you got to do each one at a time. Here's the other gotcha. All of these possibilities could be positive or negative. So every single one of them has a plus or minus in front. So we have actually 1, 2, 3, 4, 5, 6, 12 possible rational roots for our function. I do not want to do 12 sets of synthetic division to see if I can find which of these roots is actually an actual rational root. So thank goodness we've got a graph here. So here's what we have. It looks like we have a root between -2 and -3, a root between -1 and -2, and a root between 2 and 3. Well, let's see. Based on the graph then, that means 1 is out, 1/3 is out, 5 is out, 25 is out, and 25/3 is out. So the only one that we really have to look at is plus or minus 5/3. 5/3, that's really 1 and 2/3. The only one that could possibly work would be the negative one right in there. So what we're going to do is we're going to go ahead and synthetically divide out that -5/3 to see if that's an actual root. And I think I gave myself some space. I did. Let's see. So no, I didn't. Okay, I'll just do it right here. So we have, let's see, -5/3. I might give myself another page in a minute. So 3, 5, -15, -25. Go down, bring down the 3. Multiply up. 3 times -5/3 is -5. 5 plus -5 is 0. 0 times -5/3 is 0. -15 plus 0 is -15. -15 times -5/3 is positive 25. Add down, we get 0. Hey, if our remainder is 0, that means that this must be a 0 of the polynomial. And then what's left is this. So I'm going to rewrite the polynomial. I'm going to add a screen here and rewrite our polynomial. All right, all right, so we know we've got something that has to look something like an x plus 5/3, and then what's left. Now, it actually ends up being rearranged a little bit, but right now I'm just going to write it as x plus 5/3, and then a 3x squared minus 15. So going to the next page, so I have an x plus 5/3, and then a 3x squared minus 15. So I already know this 0. That one's good. Check. Let's take a look at this one. So 3x squared minus 15 equals 0. So subtract or add the 15, divide by 3, and I get x equals plus or minus the square root of 5. So it wasn't imaginary, but this is irrational. which is why it did not show up with our rational roots, our possible rational roots, because this is irrational, but it's still a 0. So our zeros for this polynomial are x equals -5/3, negative square root of 5, and positive square root of 5. Okay, next one. We only have a couple examples left, guys. Just stick with me. The number 3 is a 0 of the polynomial function. Using division and factoring, find the other zeros. So I'm going to start, if we're given that 3 is a 0, I'm going to start right away and just divide out that 3. So bringing down our coefficients here, we have 1, -7, 16, -12, and notice there's no constant term. You got to put a 0 in for it. There has to be a number for every single term. From 4, think 4, 3, 2, 1, 0. There has to be a constant term. Bring down the 1. 1 times 3 is 3. -4, -12, 4, 12, 0, 0, 0. That is our remainder. So what we have left, if we were to write this out as polynomial, I'm going to write it up here. So now we've got x cubed minus 4x squared plus 4x plus 0. So our full polynomial would be this times our x minus 3 factor. So this is our, if we were to rewrite y equals, this would be equivalent. So now, can we factor this? Absolutely, because we've got this beautiful GCF in all 3 terms. So I'm going to factor an x out. So I'm going to rewrite y equals x minus 3, just bringing that along, times x, times, now I've got x squared minus 4x plus 4. And this, of course, factors beautifully into x minus 2 times x minus 2. All right, so our zeros are at 3, 0, and 2. And notice our 2 is a repeated root. So it has a multiplicity of 2. That's okay. And then this would be our equation in factored form. So if you know a 0, divide it out. Just use synthetic division, divide it out, and then see if you can factor what's left. If you can factor what's left, factor. Factoring is always fastest. Factoring is fast. So if you can factor, factor, because it's always the best way to go. Okay, we don't need another screen for that. We're good. Okay, what is the difference between long and synthetic division? We're going to do the exact same problem again, but I'm just going to show you long division just for the heck of it. So I'm not going to do all this stuff. I'm just going to divide our factor of x minus 3. I'm going to divide this by x minus 3, but I'm going to do it using long division so that you can understand what the difference is. Long division, you don't get to use the 0. You keep x minus 3 as x minus 3. And then let's see, if you did long division when you were a kid, you write that big division symbol. And I'm going to write the whole polynomial inside of here. When you do long division, you base it on first terms. So what you're thinking about is, what is x to the 4th divided by x? What is x to the 4th divided by x? So you end up with x cubed. Or you can think, what do I have to multiply this by to get this? I have to multiply this by x cubed. So I put an x cubed up here. Now, what do? I have to multiply it, but I multiply it by this whole thing, and I put it down below. X cubed times x is x to the 4th. X cubed times -3 is -3x cubed. Here's where long division's really different from synthetic division. You subtract. Remember, you've probably done long division when you were little with numbers. We're going to do, it's the exact same thing here. You've just probably forgotten, but you subtract in long division. You add with synthetic, you subtract with long division. So x to the fourth minus x to the fourth is 0. Negative 7x cubed minus negative 3x cubed is the same thing as negative 7x cubed plus 3x cubed. So you get negative 4x cubed. Then what I like to do is go ahead and bring down the rest of my terms. All right, I have a new first term. My new first term is negative 4x cubed. What do I have to multiply x by to get negative 4x cubed? I have to multiply it by negative 4x squared. So you could also think of it as dividing. Negative 4x cubed divided by x is negative 4x squared. All right, I'm going to distribute negative 4x squared times this whole thing. So I get negative 4x cubed plus 12x squared. All right, I'm going to subtract down. So this is 0. 16 minus 12 is 4x squared. And I'm going to bring this last term down. All right, what do I have to multiply x by to get 4x squared? Plus 4x. Distribute this out, I get 4x squared minus 12x. And if I subtract down, I get 0. Now, technically, there should also be a constant term here, but again, you're just going to get a 0 when you multiply it in. So our quotient, which is already set up for us, it's the actual quotient, is x cubed minus 4x squared plus 4x. So what does this tell us? It tells us that y equals x minus 3 times x cubed minus 4x squared plus 4x. So this was my divisor. This was my quotient. These two things multiplied together equal my original polynomial. Last one, we're on the closing page. So we're going to use this, all we're doing is practicing with dividing. So we're going to divide this polynomial by x plus 4. We're going to do it using long division and synthetic division. So if I do it using long division, I'm going to do kind of side by side here. So I have x plus 4 into 8x to the 5th. There's no x to the 4th term. Put a 0 in. 0x to the 4th plus 3x cubed. There's no x squared. Put a 0 in. Plus 5x plus 7. Always have to put zeros in for missing terms. What do I have to multiply x by to get 8x to the 5th? 8x to the 4th. So I end up with 8x to the 5th plus 32x to the 4th. Subtract down, and I end up with negative 32x to the 4th. Bring down the next term. Just going to bring down one at a time. I have to multiply x by negative 32x cubed in order to get negative 32x to the 4th. And then I have minus 128x cubed. When I subtract down, I'm actually adding. So 128 plus 3 gives me 131x cubes. Then I have 0x squareds. All right, so I need a plus 131x squared times my x to get 131x cubed. And then times 4, 400, 520, 524, getting into some big, 24 big numbers here. Subtract down. So I have negative 524x squared plus 5x. Almost done, guys. So I'm going to do minus 524x minus 524x squared times 4. So first of all, it's going to be negative. All right, 2,000 plus 80 plus 16, so 2,096, 2096x. Subtract down, and we end up with 2,101 x's plus 7. Crazy problem. All right, So my final 2101, if I multiply this in, 2101x plus 4 times 2,101. They're challenging me because I didn't bring my calculator with me. So I have 8,404. 8,404. We're going to subtract down. And our final remainder here, which is kind of squishy. So 7 minus this, so I end up with negative 8,397. Now, if this is my remainder, right there, negative 8,397, if I had to write this whole polynomial, what I would actually write is this quotient minus 8397 divided by our x plus 4, because that's what's left. So this would be kind of the final term that would get added in here. All right, let's see if I can do this with less space for synthetic division. All right, so we have negative 4, because we take this, set it equal to 0, and we get x equals negative 4. All right, 8, 0, 3, 0, 5, 7. All right, 1, 2, 3, 4, 5, 6. Yes. All right. So make sure you fill in zeros for any of your missing terms. So you have to, if you start with x to the 5th, you have to go 5, 4, 3, 2, 1, 0. Bring down the 8. Negative 32. Negative 32. Let's see. 32, so 128, so 128, and it's positive, so I end up with 131 times negative 4, so negative 400 plus 120, negative 524, negative 524, all right, times negative 4, so positive 2,096. Plus 5 is positive 2,101 times negative 4 is negative 8,404. And then when you add down, you end up with negative 8,397. So our synthetic division goes so much faster, takes a lot less space. And then there's our same remainder of negative 8,397. So synthetic is usually the best way to go. Why do we learn long? I'm going to put a little page here. Why would we ever use long division? Because synthetic only works with linear factors. So the only time that I can use synthetic division is if my factors are linear. Anytime I have to divide by a quadratic or a cubic factor, I've got to use long division.